All right, so in this video, we aim to define what a linear combination is and to give an example of one. All right, so from our textbook, we're looking at definition LCCV. So this is the linear combination of column vectors. Okay, so here we're given n vectors. All right, we'll define them as U1, U2, all the way to UN, element of my Euclidean n space, and n scalars as well. So that we call that alpha 1, alpha 2, alpha n from our field of real numbers. All right, then the linear combination is the vector alpha 1, vector U1 plus alpha 2, vector U2, so on and so forth till we get alpha n, vector U n. Okay, so that is our linear combination, right? Through the definition of scalar multiplication and vector addition and whatnot, we know that this sums up to one vector, right? Whatever you want to call it, right? Let's say we call this W or whatever, right? So that is a linear combination of vectors, right? So here's our foundation here of our basic definition is foundation, as we'll see when we start to get into this idea of spanning sets, linear independence versus dependence. All this is going to be based off of this notion of a linear combination. All right, and we'll be defining further what it means to be linearly independent versus linearly dependent. Right, and we'll also see how we can set up systems of equations and interpret them as linear combinations. Right, so kind of pulling us even further away from where we started in terms of how we represented systems as just equations. And now we're looking at how we can represent them using linear combinations. All right, and in general, let's say that let's give a specific example. Let's say that we'll let alpha 1 be 2, alpha 2 be negative 1, and then alpha 3 be 4, and let's call vector U1 to be negative 1, 0, 2, U2 to be negative 3, 7, and 1, and U3 to be 0, 1, negative 1. Okay, and I can write a linear combination here of alpha 1 U1 plus alpha 2 U2 plus alpha 3 U3 to be 2, negative 1, 0, 2 plus negative 1 times negative 3, 7, 1 plus 4 times the quantity 0, 1, negative 1. Right? And that is here an example of a linear combination. And now multiplying through, we could see, all right, we can get negative 2. If we wanted to, right, wanted to simplify this, right, the way that would look would be and then adding these component-wise, right? The first element, so we get -5, -3, and -1. Okay, so we can see that we can write that linear combination as a vector by simplifying, just by applying the defined scalar multiplication and vector addition. Okay, so this is this is what we call a linear combination. All right, we start with the definition, and then we'll add some properties and come up with more definitions, more properties. But this is our foundation, right? Here's our linear combination, right? And this is going to get us into thinking about this idea of a spanning set, right? Can I come up with a set of vectors that I can write any vector in my vector space, right? So what I mean by that is, let's say, so here we have 3 vectors, and with the correct choice of scalars, alpha 1, alpha 2, alpha 3, can I write any vector in R3? All right. If so, if I can, great, right? If I can't, then what do I need to, can I add a vector in order to do that? Right? Or can I subtract a vector from here and still have a set that spans all of our 3? Okay, so we'll get into that idea, those building on those ideas. That's kind of our goal here with this idea of a linear combination. It's in order to build a set that can span a vector space, right, through linear combinations.